Okay, guys, here's another example of graphing a rational function. They give us f of x equals x squared minus 2x minus 15, and that's over x squared minus 3x minus 4. Okay, so notice this isn't nice and factored for us, so let's do that. I think the top factors as an x minus 5 times x plus 3. And the bottom we can factor as, let's see, how about a x minus 4 and an x plus 1? Okay, so we have these two different forms. Both can be useful in different ways. And down here lower, I'm going to get sort of a graph going. Okay, what I'll do is I'll do 5 ticks in each direction. And let's see what we can do. So I want to go through sort of the checklist that they got. I believe that's page 360. That checklist is on page 367, and I'm going to go through it piece by piece, okay? So just like in the last video, what I'm going to look for first are vertical asymptotes. Those are those dashed vertical lines that x can never be. Well, I know that x can never be 4, and it can be never be negative 1 because we'd be dividing by 0. So the equations of our vertical asymptotes are x equal to 4 and negative 1. We can never have that. So let's go down here. We said it was 4 and negative 1. So here's x equal to 4. We absolutely cannot cross that. And x equal to negative 1. We absolutely cannot cross that. Okay, now that's fine. That's our vertical asymptote. It's usually one of the easier ones. Horizontal asymptote, okay? Now, remember, we're asking what happens as we go off to positive infinity or negative infinity. What happens in the long run as x gets big positive or big negative? I'm hoping you read that section in the beginning of the section, that green box that talked about the different types. If you did, you'll know that when the highest degree of the numerator and denominator match, we look at the ratio of the coefficients, okay? Just to kind of reiterate on that, imagine we put in f of 100. So as we go far to the right, that would give us 100 squared. Down low, we will also have 100 squared. And I don't care about plugging it into here because in the long run, these bigger ones are going to overpower these. These are negligible as x gets very large. It's important to understand that. So if it's essentially 100 squared over 100 squared, well, that's like 1 over 1 or just 1. In fact, I could put 1 million squared over 1 million squared. It's still going to simplify to 1. Look at the coefficients here. 1 and 1, what's 1 divided by 1? That's 1 again. That's why we say when the degrees match, the highest degrees match on the numerator and denominator, then it's just the ratio of the coefficients for the horizontal asymptote. So I claim that it's y equal to 1 for our horizontal asymptote. So what I'll do is I'll go down here at y equal to 1, I'll put this horizontal dashed line. That's right here, y equal to 1. Okay. All right, that's fine. Okay. Remember now we also want to check if it crosses. Well, that's the same thing as asking, does f of x ever equal to 1? Let's see if we can figure that out. So what I'll do is I'll plug in x squared minus 2x minus 15 over x squared minus 3x minus 4, and I'm going to set it equal to 1 and try to solve for an x. If I multiply both sides by the denominator, I'm going to get something like this. X squared minus 2x minus 15 equals x squared minus 3x minus 4. Try to solve for x. If I subtract x squared from both sides, I'm going to end up with negative 2x minus 15 is equal to negative 3x minus 4. I think I'm going to be able to find an x value. Okay? So let's get the x's on the same side. I'll add 3x to both sides. So this is just solving a regular linear equation. I have x minus 15 equals negative 4. And finally, I'll add 15 to both sides. So it looks like what we're going to get here is x is equal to 11. So I go down to my graph, that's where it's going to cross. Okay, so way over here, 6, 7, 8, 9, 10, 11, there is going to be a cross right here. I guess you could say this is 11 comma 1 for our function value. Okay, so that's an idea of crossing a horizontal asymptote. Okay, so we did all that hard work with the horizontal asymptote. What else do we want to check? Okay, well, we also want to check our y-intercept. That's when x is equal to 0. So you look at our function. If I plug in 0 for all of these, I'm left with negative 15 over negative 4, or 15 over 4. Okay, so 0 comma 15 over 4, that's almost equal to 4. 0 comma 15 over 4, right there. How about x-intercepts? Remember, this is when the function is equal to 0. The easy way to check it is just to set the top equal to 0. This is the easy top to set equal to 0. X minus 5 times x plus 3 is equal to 0. Well, that's x equal to 5 and negative 3. So we're right here at 5, 0. And we're over here at negative 3. That's negative 3 comma 0. Okay, so we have all these points. Now, I think I'm ready to put it together. If the only point at which I can cross the horizontal asymptote is right here, and I'm over here, as I go to the left, where's the only place this can go? I know it's going to tend to that horizontal asymptote, but it's never going to cross. And as I go to the right here, I know it can't cross a vertical asymptote. The only place is for it to go infinitely far down. Okay. Now, like we said, this is multiplicity 1, so we expect it to flip, like in the other case. But even the fact that this is up here and I can't cross, I know it has to come from over here to hit this y-intercept. Now, I know I can't go down and cross this, so the only place it has to go is back up here. Okay. Now, from right there, the question is, what happens? Well, once again, x equal 4, that's multiplicity 1. Like I said, that's from this guy, raised to the first power. So I expect it to flip. The other reason I expect it to flip and come out this way is we have to hit this x-intercept before we get to the cross over here. So this is coming out here. I have to go up and hit this. Then I know I'm not going back over the x-axis, otherwise we'd have another x-intercept. I'm going to go, I'm going to get close, close, close. I'm going to cross because I know that 11, 1 is on the graph. But once I cross, we know as x gets really big, it's always going to tend back to that horizontal asymptote. So this is what the graph should look like. I encourage you to graph this on your graphing calculator and see that it looks somewhat like this. Some of the dips and things might not be as drastic, but it should, for the most part, look very similar. Now, the last thing I want to do is I want to talk about the domain and range of this. So if I want to talk about the domain of this function, remember that's all the x's. So I'm expecting negative infinity up to, so I'm going to the left, 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 left. I run into a problem here when x is negative 1. Cut out negative 1. Then I start back up right after negative 1. And I'm going. Ooh, I got a problem at x equal to 4. Go up to 4. Union. I'm fine anywhere after 4, forever. 4 to infinity. There's your domain. How about your range? Okay, what about the range on this guy? Okay, well, the range is asking what the y's are, so I'm going to scan it from bottom to top. I'm good until I get to, ooh, y equal to 1. Okay, that's fine. So I can go from negative infinity all the way up to y equal to 1. I can't include it though. Pick up right after 1, and then we go on forever. Now that's just depending on how low this goes. So that actually, to make a good point, is we're not exactly sure how low that goes. That's for another class. So We know about what the range is. We won't worry too much about that. We do have a good idea on the domain though. Okay. So there's another example.